Okay, welcome back. Let's do diagonalization of a matrix, giving some inspiration to the things we did concerning eigenvalues and eigenvectors. So here's where things stand. We've done determinants, and my excuse for doing determinants was to find eigenvalues and eigenvectors. We've done eigenvalues and eigenvectors, and my excuse for doing that primarily in this class is to diagonalize a matrix, though there will be plenty of other applications you're apt to run into out there on eigenvalues and eigenvectors. But our rationale has been with a focus on diagonalizing a matrix, and the reason for that is to raise matrices to powers. And we'll see exactly how that works in this section and how it intimately relates to eigenvalues and eigenvectors. Okay. So we'll define what it means to diagonalize a matrix. We'll show how matrices can be diagonalized. It's totally done in terms of eigenvalues and eigenvectors. Not all matrices are diagonalizable, we'll see as well. But once a matrix is diagonalized, if it can be diagonalized, then it's a piece of cake to raise that matrix to powers. So this will allow us to go back and address that application concerning the Fibonacci sequence that we used to motivate this whole chapter back in section 5.1. And we'll see that dealt with in detail in section 5.3. Recall a matrix is diagonal if all the entries off the main diagonal are 0. So we got a square matrix. It will be diagonal if it's both upper and lower triangular, so there's only zeros below the main diagonal. There's only zeros above the main diagonal. Nobody said the main diagonal itself couldn't have zeros as well, but there's zeros off of the main diagonal only. Only zeros off the main diagonal. Okay, so the plan is do what we can with real numbers. These theorems from this section are valid whether we use real numbers for entries in matrices and entries in vectors. They're also valid for complex entries and complex scalars. This has been an issue we've pushed aside until now, and we'll still largely bury it. In chapter 9, there's a good deal of information about vector spaces where the numbers are complex and the entries in the vectors are complex. So instead of looking at the vector space Rn, we might look at the vector space Cn, where C represents the complex numbers. Here's the reason this comes up at all. It's the fault of the fundamental theorem of algebra. So throughout this section, what we say will hold for matrices with complex entries. We'll stick in this section to computations involving real numbers, though even when you're interested only in real numbers, these complex numbers can still play a role. You'll see this maybe in a differential equations class. We're forced into this because, if you'll recall, the characteristic polynomial of a matrix was an n-degree polynomial, and the zeros of the characteristic polynomial were the eigenvalues of a matrix. So zeros of polynomials are tied in with eigenvalues. That's why we're interested in them. Unfortunately, a perfectly decent polynomial with nothing but real coefficients can still have imaginary roots or complex roots, meaning sometimes even when everything is nice and real in the question, complex numbers are unavoidable. Complex numbers will arise as eigenvalues. Fundamental theorem of algebra says that P of x is a polynomial, say a sub n x to the n plus a sub n minus 1, x to the n minus 1, and so forth down to an x squared term, an x term, and a constant term. If this is an n-degree polynomial with either real or complex coefficients, in chapter 5, it'll be real coefficients. Then P can be factored as P of x equals a sub n times x minus r1 times x minus r2 up to x minus r sub n, where R1, R2, and R sub n are the roots of the polynomial. So we factored this n degree polynomial into a product of n linear terms. You might call them linear terms. You saw this kind of thing in Calculus 2 when you were integrating rational functions. You expressed the denominator as a product of linear terms and irreducible quadratics. What made them irreducible was they didn't have real roots, but they had complex roots. Here, we're allowing these roots, R1 through R sub n, we're allowing them to be complex. And the fundamental theorem of algebra says, then you can totally factor a polynomial into a product of linear terms using complex numbers, which you didn't do in Calculus 2. And that's the reason you had irreducible quadratics in Calculus 2 when you were dealing with integrals of rational functions, when you did that partial fraction decomposition stuff. Well, there'll be nothing but linear terms if you let me use complex numbers. And we can just go pick off the roots of the polynomial if it can be factored like this. They're R1 through R sub n. They may not all be different. The first example we did, it was a second example we did of finding eigenvalues. We had 4 appear as an eigenvalue of multiplicity 3. So it was repeated 3 times. We had the same linear term repeated 3 times when we factored the characteristic polynomial. It was, I think it was the previous section. These roots may not be distinct, as we saw there, and they may be complex. Even when you start with real coefficients, which we will in this section, in this chapter, you still may get these complex numbers to arise. And in this chapter, they play the role of eigenvalues. But the fundamental theorem of algebra tells you, hey, you got an n degree polynomial, like the characteristic polynomial, it's got n roots. They may not all be different, and they could be complex, but any polynomial of degree n with real or complex coefficients has n roots, can be factored as n linear, a product of n linear terms. All right, the characteristic polynomial, determinant of A minus lambda I. If A is an n by n matrix, as we've seen, that's an n degree polynomial. So fundamental theorem of algebra tells us we can find n eigenvalues. They may not be distinct, we've seen that in an example, and they may be complex, and we haven't seen that in an example. What we'll do with complex eigenvalues, at this stage, we're probably mostly going to ignore them. If we could deal with complex numbers and not be so emotionally attached to real numbers, things do work out a whole bunch cleaner if you can use the complex values. And they are unavoidable even if you stick to inputs that are real. If you stick to matrices with real entries, there's still a possibility you're going to get complex eigenvalues and maybe eigenvectors as well. Those vectors must live in Cn and not Rn. I leave it to you to hack through chapter 9 on the details of that. It's really cleaner if you'll use complex numbers. A lot of algebra is cleaner if you'll use complex numbers, it turns out. Recall that the multiplicity of a root of a polynomial is the number of times the factor x minus r appears in the factoring of the polynomial. Like we saw with that x minus 4, that was a factor 3 times. It was x minus 4 cubed. When we were dealing with that example of finding eigenvalues for polynomials, and 4 was the only eigenvalue, but it had multiplicity 3 because we had it the characteristic polynomial factored as x minus 4 cubed. So we'll run across this multiplicity idea again, and it will be related to when we can and when we can't diagonalize a matrix. Okay. The following theorem is totally fundamental in diagonalizing a matrix. It relates how a matrix is diagonalized to eigenvalues and eigenvectors. So, okay, here's motivation for finding eigenvalues and eigenvectors. The statement here has you being given eigenvalues and eigenvectors. Okay, well, we've seen we can find those things if we can perform the algebraic computations, which sometimes we can't because we won't want to use complex numbers. And pragmatically, other times, because it's hard to factor polynomials, we'll do clean ones where we are able to do the factoring. So theorem 5.2, matrix summary of eigenvalues of a matrix A says, let A be an n by n matrix. This diagonalization stuff is only a conversation we would have for square matrices, just like the conversation about eigenvalues and eigenvectors, and just like the conversation about determinants, because it turns out these things are based on each other. So only square matrices. A is a square matrix, an n by n matrix. Let lambda 1 through lambda n be the eigenvalues of that matrix. Excuse me, let them be values. We're going to make a claim about them being eigenvalues and that relating to diagonalizability. So we're taking lambda 1 through lambda n, excuse me, just to be scalars at this stage. Maybe complex. And we're taking v1 through v sub n to be vectors of n dimensions. They've said n space here. They're being a little elusive on what they mean by n space. Some details to follow on that shortly. Rn is certainly an example of n space. So is Cn, where we use complex numbers. Whether or not we're dragging complex numbers into the story puts a different meaning on what n space is. Let C be an n by n matrix having v sub j as the jth column vector. So we've chosen these vectors, whatever they are, to be columns vector C. Maybe should have emphasized these were non-zero vectors, because we'll talk about these vectors being eigenvectors, just as we'll talk about these scalars being eigenvalues here shortly. So we're taking matrix C by putting this collection of vectors into matrix C, using vectors as columns. Vectors as columns is a familiar operation. And we're creating a diagonal matrix D, n by n, by putting zeros everywhere except along the diagonal. We're putting these scalars. Then we have the following relationship. Matrix A that we started with times matrix C, which was created with these vectors, equals matrix C, we created earlier, times matrix D, as given here. We get this equality in matrices, never mind why we want it, but we get this equality between those matrices A, C, and D, if and only if the lambdas are eigenvalues of A and the v sub j's are corresponding eigenvectors of A. So never mind just yet why we want that relationship, but this is an intimate relationship on the road to diagonalizing a matrix. And well, it involves a diagonal matrix. At least we got that going for us. But the claim is we'll have this matrix equality when and only when we use eigenvalues and we use corresponding eigenvectors. Let's look at the proof of that, because we want to know why it's true. And it's actually fairly straightforward computation. Okay, so let A be an n by n matrix with the lambdas and the v's. Anything initially, we need to show we get the equality AC equals CD when those lambdas are eigenvalues with corresponding v's as eigenvectors. And the only time we get that equality is when the lambdas are eigenvalues and the v's are eigenvectors. So it's two claims. Okay. Let's compute C times D. C was the matrix, using the textbook's notation here. C was the matrix that had as its first column vector V sub 1, vector V sub 2 is its second column, its nth column, vector V sub n. We put these little ellipses above and below the vectors to indicate they are columns of the matrix. And we had defined matrix D to be exactly this diagonal matrix. All right, if you'll do your row times column thing, let me convince you of this, of maybe at least the first column. We're going to take, let's look at the first column. We'll take the first row times the first column. What we'll get here, first row will consist of the first component of that first vector, first component of the second vector, and so forth. So it'll be all first components along the first row. First column, we'll multiply that first row times this first column, dot product style. We'll get lambda 1 times the first component of v sub 1, and then zeros. Zeros below that, so we'll get zeros times those other first components. So in the product, up here in the upper left, we'll have the entry lambda 1 times the first component of the first alleged eigenvector. Let's do the second row. Second row will be all second components. Second row, first column, we'll get that second component of eigenvector v sub 1, alleged eigenvector v sub 1, times lambda 1. So over here in the 2, 1 entry, we'll have lambda 1 times the second component of vector v sub 1, and so forth. Down to where we go along the last row, you'll have the last component of v sub 1 times lambda sub 1 and a bunch of other zeros. And indeed, along that first column, you'll have lambda 1 times the first component of vector v sub 1. Then you'll have lambda 2 times the second component of v sub 1, down through lambda sub 1 times the last component of v sub 1. This first column will simply be lambda 1 times the components of vector v sub 1. And similarly, if we looked at what happens over here in the second column of the product, we'd see what happens in the second column of the D matrix. And it's going to go through and introduce lambda 2s, and they're going to hit the components of the vector v2. And we'll similarly see each of the columns in that product will be lambda 1 times vector v1, lambda 2, vector v2, and so forth. Okay, so we want to see when AC equals A times vector C. So the only time we'll have that equality is when, all right, let's see, we'll look maybe at how vector A acts on this. If we apply vector A to this C matrix, we'll have vector A times the first vector, v sub 1, that'll be the first column in the product. Vector A times the second vector will be the second column, and so forth. When we first encountered products of matrices, we made an observation that what we'll get in the product will be this matrix applied to, say, the second column of this matrix as the second column of the product AC. Well, here the second column, for example, is lambda 2 v sub 2. So the only way we can have equality of AC with this CD stuff, so equality implies that lambda v sub 1 equals matrix A times vector v sub 1. Lambda 2 v sub 2, A times vector v sub 2. In general, A times v sub j equals lambda sub j times v sub j. So we get that equality if and only if we get this relationship here between matrix A and the vectors v sub j and the scalars lambda sub j. Well, that rings a bell. That's totally eigenvector and eigenvalue stuff. In other words, we're getting equality if and only if this occurs. Remember, the vectors v were non-zero vectors. That was in the hypotheses. So these vectors v, they are eigenvectors with corresponding eigenvalues lambda sub j, and we get the relationship to hold with the equality if and only if the columns are the same. And being the same in terms of columns is this eigenvalue eigenvector relationship. So why ever you would want AC to equal CD, where we've introduced C and D the way we did, well, it's only going to work when we get a relationship that says the lambdas are eigenvalues and the vectors v are eigenvectors. Okay, back to the notes. See why we'd want to do that. Well, here's one. All right, so we're approaching what it means to diagonalize a matrix. I'll give away a bit of the hint here. We're going to solve that equation we had, here it is, AC equals CD. We're in a sense going to solve for the diagonal matrix D by taking C inverse and multiplying both sides by C inverse. So that'll produce the diagonal matrix written as a matrix equality. But wait, how do you know matrix C is invertible? So that's why we need a little prerequisite conversation here. The n by n matrix C is invertible if and only if, I guess Theorem 2.6 said this, if and only if the rank of C equals n. Good for Theorem 2.6. Does it make any sense? See, the rank, what? The rank is the number of pivots we'd have if we took that matrix C and put it in reduced row echelon form, or row echelon form. How would you find the inverse of matrix C? You'd augment it with the identity matrix and try to turn C into an identity matrix. And what happened on the other side of the augmentation would produce C inverse. So whether you remember the stuff about ranks and number of columns is what it really is, and dealing with invertibility with square matrices, whether you remember Theorem 2.6 or not, you know this result. And you know it because you know how to find inverses of matrices. Matrix, augment with identity, do your row reduction thing. If it works, the matrix is invertible. If it doesn't work, the matrix isn't invertible. When's it going to work? When you take C and reduce it down to the identity matrix. Well, then C will have rank n. That row reduced version will have n pivots, n by n matrix. So there you go. So you knew this, whether you could piece together rank and linear independence and all this other stuff or not. You knew this result based on the fact that you know how to find inverses of matrices. All right. So let's see, C is invertible if and only if the column vectors of C form a basis of n space. That was mentioned maybe as well in terms of Theorem 2.6, but basis. Yeah, the rank of a matrix was it? By definition, it was the dimension of the column space. We knew how to compute it using row reduction, but it was given by definition to be the dimension of the column space. Oh, well, you've got the columns of matrix C being vectors from n space. There they are being elusive about what that means again. But n-dimensional vectors with scalars from somewhere. The reals are the complexes. So they're trying to be liberal with this and allowing this to be a statement that works for both real and complex. But if the rank is n, then the dimension of the column space is in, because that's the definition of rank. Okay, well then those n columns must be a basis for n space since the rank is n. So that, in some sense, you knew that as well. We've covered this before. What's a basis? Linearly independent spanning set. Okay. You know you've got the linear independence when you have a pivot in every column. You did the row reduction stuff. It might ring a bell. That's how we showed linear independence a chapter or two ago. And then if we know the rank is in, then the dimension of the space generated is in. So it generates the whole n space, whatever that is. And this collection of vectors is linearly independent. That's what a basis is. So all the pieces are there. The cheap way of authoritatively stating it is that Theorem 2.6 gives you all that. But deep down, you know this stuff based on how you do computations and the kinds of problems we've done. Anyhow, so if the rank is in, then we've got a basis of n space. In that case, that matrix C is invertible, and you know how to find an inverse, and it's related to all this other stuff. So as long as rank of C is n, then we've got invertibility of C, and then we can take the equation. This is the real goal. AC equals CD. We can take that equation and write it as D equals C inverse AC. So solve for D, multiply both sides by C inverse on the left. So the way they word it is this equation transforms matrix A into a diagonal matrix D, along with some extra decoration. You got this C and C inverse on there. They claim it's easy to raise this thing to powers. And that's ultimately what we wanted to do. That's how we motivated this stuff. One more definition, and then we'll look at a result or two, and then finally do an example to illustrate this stuff. It'll be mechanical when we do the example. All right. N by N matrix A is called diagonalizable if there exists an invertible matrix C such that C inverse AC equals D. I've chosen to write it like this. They've got D on the right-hand side instead of the left-hand side, but that's equivalent to what we have here. So being diagonalizable means you can find a matrix C, an invertible matrix C, and a diagonal matrix D where this equation works. And you know, if you'll piece the last two results together, that's only going to work out when C has as its columns eigenvectors of matrix A, and D has as its diagonal entries eigenvalues of matrix A. Under these conditions, matrix C is said to diagonalize the matrix A. So diagonalizable means you can write matrix A like this. And you know from the first theorem, the only time that's going to work is when you use eigenvalues in D and eigenvectors for columns of C. And that doesn't tell you directly what C inverse is, but you could figure it out. It does exist. All right, let's look at the first corollary. The second one's a touch more important in my opinion. First corollary says, an N by N matrix is diagonalizable if and only if N space has a basis consisting of eigenvectors of A. Okay. Suppose A is diagonalizable. Then we know that means C inverse AC equals D for some invertible matrix C, the definition we just had. Okay, let's take that, multiply on the left by C. Okay, we'll get the C times C inverse to produce an identity. We'll be left with AC on the left. We pick up a C on the right. We get AC equals C times D. That's why we looked at theorem 5.3. Theorem 5.3 says the only time that's going to happen is when C is made out of eigenvectors of A and D has its diagonal entries of lambda 1 through lambda n. And we put the eigenvectors of C in corresponding positions to the location of the eigenvalues in D. If you put lambda 1, is that 1, 1 entry in diagonal matrix D, then you've got to take vector v sub 1 as the first column of matrix C. So do these in corresponding position is all that means. We've got C invertible that was given as hypotheses. You were told A is diagonalizable. That means there exists an invertible matrix C, so we don't have to show that. But when C is invertible, then the columns of matrix C span in space. Theorem 1.112. This is that conversation we were having about linearly independent and rank. So I could express this in terms of linear independence and ranks, but this is what we were just describing. So the span of the columns is all of n space. And again, these guys are being cagey about what n space is. Is it Rn? Is it Cn? Well, it's Rn if you can do it all with real numbers. And if you can't, you need some complex numbers, then it's Cn. There's a little, if you really like mathematical details, a little bit of concern over the fact that Theorem 1.12 only was valid in the real setting. We need a version of Theorem 1.12 for the complex setting. Let's let that ride, though. It's based on the fact they're both fields. R and C are both fields or something like that. Okay, so let's see. In space has dimension n. The column vectors of C are a set of n vectors which span it. You know those vectors are linearly independent because the rank is in, because C is invertible. Theorem 2.3, I guess part 3a or something also justifies that. So we've got a linearly independent spanning set. That's what a basis is. So if we have A is diagonalizable, then that matrix C must consist of a collection of eigenvectors that form a basis for n space. That was half of the claim. The other half of the claim was, suppose n space has a basis consisting of eigenvectors of A. All right, so now we're doing it the other way around. Will be done, I see it in the shadows, when we get the C inverse AC equals D stuff this time. And we assume that in the previous one, we're proving the converse. Okay, conversely. So suppose the V's are eigenvectors and they have corresponding eigenvalues, lambda 1 through lambda sub n. All right, well, we know that bases are linearly independent sets. So the vectors V1 through V sub n, they must be linearly independent. So if we make a matrix C, the way we're going to make matrix C, by having the jth column of C to be the jth eigenvector up here. All right, we know those eigenvectors by hypothesis form a basis. Bases are linearly independent spanning sets. It's the linear independence part we need right here. Hey, when the columns of a matrix are linearly independent, that matrix is invertible. How many different things can you tell me that's equivalent to a square matrix being invertible? The rank of the matrix is n, if it's n by n. The vectors are linearly, column vectors are linearly independent. The determinant is non-zero. There was a bunch of stuff, but one of those involved linear independence of the columns. I guess it was Theorem 1.12. Okay, so we do have then that matrix C is an invertible matrix. All right. We know if we create matrix D using as the diagonal entries, little d sub jj, the diagonal entries of matrix D to be the eigenvalues, then we will get A times C equals C times D, because we've used eigenvectors for the columns of C and eigenvalues for the diagonal entries of D. C is invertible. We just had that conversation. So we can multiply both sides on the left by C inverse to produce C inverse C, some cancellation there, to produce C inverse AC equals D, and that's what diagonalizable means. So this result, let's go back to the notes, tells you, to the notes, diagonalizable if and only if n space has a basis consisting of eigenvectors. And what are you going to do then? You're going to do really what you were told up here. You're going to make matrix C using eigenvectors, and you're going to make matrix D using eigenvalues. All right. Why would you want to do all this? That's what Corollary 2 is about. Corollary 2 says, so you want to raise matrix A to a power. We talked about this and motivated this when we looked at the Fibonacci sequence. Okay, let's read it over here in the supplement. All right, it says, let A be an n by n matrix, let it have n eigenvectors and eigenvalues, giving rise to matrices C and D, like we've had above. And we know we can write the equation C inverse AC equals D. Probably I inserted some of this additional verbiage here. A diagonalizable matrix means this. Then we can compute a to the k is c d to the k c inverse. All right, here's why. Computationally, it's a piece of cake. I need to convince you probably this is useful still. All right, so let's see, we know we can write, we'll take the relationship C inverse AC equals D. We can solve this for A. Take the C inverse to the other side on the left, take the C to the other side on the right. That'll produce A equals C D C inverse. So we're solving this equation for A instead of D, and we'll get A equals C D C inverse, C D C inverse. So if we want to raise A to a power, that's the same as raising C D C inverse to that power. A to the K is C D C inverse, C D C inverse, and so forth, K times. And look what happens. This is the punchline. The C inverse and the C, they're side by side. So we can use associativity to rearrange this product and get C, D, C inverse C, grouping those two together. D, C inverse C, grouping together the C inverse and the C that follows it. D, C inverse C, D, C inverse C, D, C inverse C, D, and the final C inverse. All in C inverse C's are going to become identity matrices, except for the first C and the last C inverse. Can't move things around. We don't have commutativity, remember. All those identity matrices we can ignore. They're identity matrices, so they can be dropped or absorbed in the D's. And we get C, D times D times D times D, K times C inverse. We get C, D to the K, C inverse. So raising A to the K power, if A is diagonalizable, is equivalent to this computation here. That's the punchline. Let's see if I can convince you this is worthwhile. So you've traded the question of raising A to the K power for raising D to the K power, and then a little bit of matrix multiplication. You good at matrix multiplication? Row times column stuff. It's tedious, but it's straightforward and not a whole bunch of computations. You only have to take two matrix products. But are you better off? You know how to raise D to the K power? D's a diagonal matrix. Let's take a look at it, what we had upstairs. Yeah, here's matrix D. What if you were to square matrix D? I think we foreshadowed this probably with some homework or some exercises or some examples in the past. Well, if I was to take this matrix and multiply it by itself, we'd do first row times first column. That'd give us a lambda 1 squared. First row times second column, because of all the zeros, that produces 0. First row, any other column, all zeros. The only time we don't get 0 out is first row, first column. Third row, first column, zeros. Second column, zeros. Third row, 0 squared plus 0 squared plus lambda 3 squared plus 0 plus 0 plus 0. So to square this matrix, what you're going to get is D squared equals lambda 1 squared, lambda 2 squared, lambda 3 squared, through lambda sub n squared along the diagonal, and zeros everywhere else. So it's easy to square, or in general, raise a diagonal matrix to a power. You just raise the diagonal entries to a power. That's why you wanted a diagonal matrix. Are matrices easy to raise to powers? If they're diagonal, yes. If they're not diagonal, no, but there's sometimes a shortcut. Sometimes they are diagonalizable. And when they are, then yeah, it's easy to raise matrices to powers. Not as easy as just diagonal matrices, but to raise A to the K power, we'll take D, raise it to the K power, piece of cake. And we'll multiply on the left by C and on the right by C inverse. How long is it going to take us to do this? Well, you got to find all the eigenvalues for matrix A. You got to find a set of eigenvectors for matrix A. And you got to find C inverse. Okay, that could be a bit time consuming, but it's quicker than taking k as 100 and multiplying this little matrix A times itself 100 times. So it is worth the trouble to go through and do this, and we get it for arbitrary k. Let's illustrate it. All right, this will be a bunch of computations. I'll gloss over the computations. It's stuff we've done so much before. But let's see what's going on in this example. Story is, take this matrix, diagonalize it, and raise it to the k power. Okay. All right. Diagonalizing. We're going to need eigenvalues and eigenvectors. Eigenvalues, this is all news to you. Okay, we need a minus lambda I, so we'll subtract lambda along the diagonals. We'll take the determinant of that. That'll give the characteristic polynomial. It's a 2 by 2 matrix, so it ain't so bad to take the determinant. That will produce, after some computations, this second degree polynomial, which is fortunately easily factored, and it doesn't involve complex numbers. Okay, here's a characteristic polynomial. Eigenvalues would be the lambdas that make the characteristic polynomial 0. So a -1 would make this factor 0. A +8 would make this factor 0. Let's denote, as we have done, denote those eigenvalues as lambda 1 equals -1 and lambda 2 equals 8. Okay, so we found the eigenvalues. 2 eigenvectors. Okay, so let's see, we'll have to find the eigenvectors for both of these. That'll mean solving a system of equations. That system of equations will have a free variable every time we do this, or else you've done something wrong. That's where the lambdas came from, ensuring us there will be resulting systems of equations that have free variables. Okay, so for lambda 1 equals -1, let's look for an eigenvector. Let's call it v sub 1 vector. Let its components be v1 and v2. We'll have to treat it as a column vector to get the system of equations notation correct. Maybe not quite right and all that stuff out though. All right, so let's see, we'll take the system of equations, a minus lambda I times that eigenvector equals 0. In this case, lambda is -1. All right, so we'll have a minus -1i, which means effectively minus a negative, adding 1 to the diagonal entries. So we've taken matrix A and added 1 along the diagonal because of the minus lambda stuff. We need to solve this system of equations, row reduce it. Ta-da, we got a free variable in the second column. You better have a free variable or something's wrong. That free variable will lead us to eigenvectors. So, you know the story. We'll convert that back into a system of equations. We'll solve for v1 and v2. We'll replace the free variable. We'll replace the v2 with a parameter. I've done a little trick here and sucked up the 1/2. Let's let r equals v2 divided by 2 be the free variable, in which case we won't have a fraction here. Here we want v sub 2. Well, v sub 2 is 2 times r. So we'll get r and 2r for v sub 1 and v sub 2 respectively. If you don't like it, you go right ahead and you let r equals v sub 2. You'll have halves up here. I don't have halves up here. I have 2's down here. It's the same collection of vectors. The book, in the solutions manual and in the back of the book, they frequently do this to bury these, to bury the fractions. So well, for the sake of variety, let's do that substitution. If you don't like it, you don't do it that way. You'll get the correct answers. I really do want to avoid fractions because we're going to be inverting a matrix here somewhere down the line. So anyhow, we get then that the vector v must be of the form r times a vector with first component 1 and second component 2. R can be anything. Can't let r equal 0 because 0 vector doesn't count as an eigenvector. So here's the complete collection of eigenvectors associated with lambda 1 equals -1 eigenvalue. We need one of them. How about we let r equal 1, we'll take the vector 1, 2. You want to let r equals 2 and take the vector 2, 4, that, good, knock yourself out. That'll work as well. We just need an eigenvector. You want to use 1/2, 1. That's what we get with r equals 1/2 here. I don't recommend it because the 1/2 stuff will come back to haunt you when we're inverting matrices down the roads. Hey, you get to choose any value of r you want, even if you got fractions here. Now you can choose r big enough that the fractions are eliminated. Let it be the least common multiple of the denominators. You can get rid of the fractions at this stage when you wish to pick individual eigenvectors. And that's what we'll need for the columns of matrix C. On to the second eigenvalue, okay, 8. We'll consider the system of equations, a minus lambda I times the second vector equals 0. So this is a condition for v sub 2 to be an eigenvector associated with lambda equals 8. There's the a minus lambda, a minus 8 along the diagonals. Produces this, row reduces to this, pivot-free column. If there wasn't a pivot-free column, something's wrong. Turn it into a system of equations, introduce a free variable, a little less details on this one. And that produces the fact that v2 must be of the form s times negative 1, 1. S is any real number except for 0. All right, maybe we could let s equal 1, and that would give us a particular nice eigenvector associated with lambda 2 equals 8. All right, so we'll choose r and s the way I set things up, both to be 1. You want to choose different things, go ahead. This is one of those deals where, well, you got an infinite number of choices for the eigenvectors. Choose wisely, choose small whole numbers, small integers. Otherwise, the arithmetic's going to be messy downstream. But you do have a liberty to choose things other than v sub 1 and v sub 2. So this is why we do a test on this. I can't do the row reduction for you because I don't know what you're going to choose for v sub 1 and v sub 2. It depends how you went through your system of equations. So some of this must be dealt with by hand or software. So anyhow, I choose v1 and v2 as given. Infinite number of choices, but I'm setting my free variable r and s equal to 1, both of them. That produces these. So for the matrix summary of the eigenvalues of A, we'll take C to have V1 is its first column and V2 is its second column. So that'll produce this. Here's the book's notation for that. Here's matrix C. And diagonal matrix D, we'll have lambda 1 and lambda 2 along the diagonals. The lambda 1 has to come first because you put the corresponding eigenvector associated with lambda 1 in the first column. So the negative 1 has to come first and the 2 has to come second. You want to swap the order up here, you'll have to swap the order down here as well. So again, I can't say there's unique solutions to this. We can permute some things around, permute columns around, is what it amounts to. But anyhow, then there's the C and the D. We're guaranteed we'll have AC equals C times D. That's what Theorem 5.2 told us. All right, so we still need C inverse to diagonalize is to find C, D, and C inverse. Okay, so here's C, 1, 2, negative 1, 1 as columns. We'll augment that with an identity matrix and find C inverse. And it looks like we get, got some fractions in there. We've got them isolated at least. So it produces something like this for C inverse. Let's factor that 1/3 out. That way it kind of looks like I've only got one fraction, when in fact, arguably I've got 4 of them, but I've got it isolated. I've got the 1/3 isolated. So if that's C inverse, then we've got A diagonalized as A equals CD C inverse, or we can write, I guess, D equals. This is more appropriate for diagonalizing matrix A. A equals CD C inverse. C we found a couple of slides back. D we found a couple of slides back, and here's C inverse that we just computed. So there's matrix A diagonalized. They also wanted us to raise A to the kth power. Okay, big example coming. Let's raise a to the kth power. We know by corollary 2, that's the same as taking c times d to the k power, c inverse. All in c inverse is canceled, as we saw in corollary 2. Okay, here's c, here's d to the k power, here's c inverse. Somebody told us scalars pull through on this kind of stuff, and take that 1/3 all the way out front. You know how to raise a diagonal matrix to the kth power? You do. You just put the exponents on the diagonal. That was the whole point of getting a diagonal matrix. So we did what we did to get from this step, to raise to the kth power a diagonal matrix instead of matrix A. All right. Now we need to do our row times column stuff to get this as a single matrix instead of a product of 3. So we'll do our row times column stuff. Okay, let's see. I've got some -1s to the k's and some 8 to the k's. We'll just leave it in terms of k. We don't have much choice because you don't know what k is. Do some more matrix multiplication, row times column stuff, and we'll produce this matrix here, and there's a to the k power. You give me a value of k, all I got to do is plug it in these things here and determine what the entries of a to the k power is. You can simplify this. I don't think so. Maybe quick little observation. -1 to the k, well, that's either going to be 1 or -1. If k is even, it'll be +1. If k is odd, it'll be -1. So the -1 stuff, arguably I could write that a little bit different, but I'd have to break it into cases of k even, k odd. This is the cleanest way to present the solution. And there's you. In this one example, 5.2.a, an example of diagonalizing. You see how it involves eigenvalues, how it involves eigenvectors, how those involve determinants, that's where the eigenvalues came from, and systems of equations, some of the stuff we did back in chapter 1. So this is a real synthesizing moment where we glued all that stuff together. So let's take a little breather and start a second video for the remainder of this section. I'll see you in a few minutes.